because sometimes it thinks my monitor computer is the boss computer. I don't know why, but it does. And I never know whether it's when it's going to do it or when it's not going to do it. But I found that this way that I'm doing it now seems to work the best. Maybe. Okay. All right. All right. Almost ready. Okay. And take off the co-host. All right. So let's do the daily two. You guys can stay on your Chromebooks just for a short time, and then we won't use them anymore. So I'm going to share the screen and let's look at what we needed to do for today's daily two. And that is right here. So sphere A has a charge of positive Q on it. You bring it into contact with identical but neutral sphere B. The spheres are then separated. You then touch sphere B with your finger, touch sphere A again, and then separate. What is the charge on each sphere? So we had to wonder about charge distribution. Okay, and so I'm gonna stop sharing now. And so let's diagram this. Let's map this thing out. All right. So we have sphere A. I'll call this. Well, let me write this one here lower. So I have sphere A and sphere B. Sphere A has a charge of plus Q on it. Sphere B is identical but neutral. Okay. Now we're going to touch them. And when we touch them, they're going to share charge. And if they're identical, then they're going to split it evenly. So I'm going to get Q over 2 there and Q over 2 there. Okay. That makes sense so far? All right. Okay. Then what happens is we're going to separate them. And so they're going to keep their Q over 2 charge. All right. And then we're going to touch them. We're going to ground one of them. And when you touch it with your finger, it's the same as connecting it to the earth. Okay. You're going to, and you are an unlimited supply or an unlimited dump for charge. And so when you touch it with your finger, all this charge on there is just gonna leave. It's gonna go into you. Okay. And so when you ground it, you neutralize it. All right. So what you're going to end up with then, moving it over here, sphere A and sphere B. After you're all done doing that, okay, sphere A will still have the positive Q over 2 charge on it, but sphere B is now back to neutral. Okay. Okay so far? Yeah. All right. And then any questions on for those of you at home? Put them in the chat window if you have a question. All right. Not seeing any questions. Okay. So then when we touched it again, when we it's too large. When we touch them again, once again, they're gonna split charge, and they're gonna split it evenly. All right. I'm never going to give you a case when I have a large sphere and a small sphere. That's way too complicated. Okay, the spheres are going to be the same size, and so they're going to split it evenly. So this Q over 2 is going to split even once again. We're going to have Q over 4 there and Q over 4 there. And then when you separate them, they're going to keep that charge, and that's the answer. So they're going to have positive Q over 4 on each charge, on each sphere. Sorry. All right. That make sense? Make sense? Yeah. Okay. Makes sense at home? All right. So when I ask you a question like this, think two things. If you touch them, then they share charge equally. Okay. And then if you ground, if at any time you ground it by you touching it or connecting it to the earth, then all the excess charge on that object is taken off. Okay. The earth or you are an unlimited supply or an unlimited sink, they call it, sink for electrons or charge. Okay, and we're assuming here that positive charges can move, and you can assume that in this kind of case. Okay. Okay, that's daily to number 1. Questions? when the charge is split evenly, are you sharing those two positive charges? Yes, we can assume, yeah, Mr. Artis, you told us that positive charges can't move, they're locked in the nucleus. Yeah, true. But for the purpose of this, we can assume that positive charges move, okay? What really happens is when you touch a negative charge, will go for the neutral to neutralize some of the positive charge there, yeah. But it's gonna end, we can think of it as if positive charges move, okay, in this particular case. The net result of that, the end result, is that they end up with the same amount of charge on each. And if they start out with this, they're going to split it half and half. Okay, and then half and half again later. All right. Other questions? The two positive charges split into 1 and 1. Yes, you can think of it like that. You can think of it like that. If you want to think, okay, start out with 2, and then they're going to end up with 1 and 1. You could think about that. But I would advise using a slightly larger number, you know, maybe 20, and then they're going to split into 10 and 10. Because later on, if you split it again, you can split them, you know. So I would suggest something like that. Actually, if you want to think, I would choose 24 because it splits 2 ways, it splits 3 ways, it splits 4 ways, you know, a lot of factors. If you want to put numbers on it, that's what okay.
I think imagine like just ratio line. Like the ratio is not be 1 to 1. But,
oh yeah, 1 to 1, sure. Somebody offered, Jack offered. They think ratios too. Yeah, that works perfectly. Whatever works for you, you know. Whatever works. All right. And then the next one was a Ohm's law and power problem, and it said, let's see here, a voltage of 120 volts is put across the light bulb. So, some room to work here. So I have a voltage of 120 volts, 120 volts, and a current of half an amp results. So I get half an amp. Okay, first question. Find the resistance of the bulb and the power. So find the resistance. Okay, we can use Ohm's law for that. All right, let's see here. I'm solving for R, so that involves dividing out the I. That one's dead. That one's dead. Dividing out the I, so pretty much dead also. And what we get out of that is that R is equal to V over I, which is 120 volts over half an amp. 120 divided by 0.5 is 240. So the resistance is 240 ohms. 240 ohms. Okay. It's your basic Ohm's law problem. And let's see, how'd you guys do on that one? Lots of correct answers, some not so much. So questions? Very typical problem that you might see on the test next week. Okay, and then the power for part B, it also asks for the power. So P is equal to I times V. That's the power equation. Current of a half an amp, voltage of 120. So we get, let's see, half an amp times 120 volts, and a half times 120, 60. And the unit for power is the watt. Okay, named after an English guy by the name of James Watt. And we can abbreviate that capital W. So there's your power there. Okay. All right. Okay. Oops, is that on camera? Put my monitor camera here. Is that on? All right. Questions, comments? All good? All right. Just a couple of equations that pertain to electricity. Okay. All right. Well, the main topic of the day, is one of these, okay? A battery, all right? I'm gonna spend about, I don't know, 20 minutes, 25 minutes talking about these. the electric battery, a portable source of electrical energy. Okay. Now, these are about 200 years old. That is, they were invented in the first decade of the 1800s. And they were invented by this guy. They're invented by this guy. Okay. A guy by the name of Alessandro Volta. Alessandro Volta. Okay, he was Italian. Italians have very musical names. Alessandro Volta. Okay. And he invented the electric battery. And the way he did it was he took a wafer of silver and a wafer of zinc. And he put paper that was soaked in salt water between them. He made a sandwich with salty paper in between. And when he connected the two discs, the two wafers, he saw a little spark. Okay. And the net effect of all that was there was a potential difference between the plates when they were separated by saltwater soaked paper. Right. So that was the first battery. And if you make a double decker, triple decker, if you kept making what's called a voltaic pile, the potential difference increased. And that was the first electric battery. Okay. Although there are some stories that ancient Egyptians had invented batteries like a couple thousand years ago, but that's up for debate. But the first practical one, well, that's not saying those aren't practical, but the ones that developed into these were first developed by Volta. Okay. And so over the years, they were perfected, and now we end up with one of these. Now, what do these look? How do these work? Well, I have a little presentation or just a diagram that I'm going to recreate up here. And so, but if you're interested, it's in the. Actually, why don't you guys take a look? Or I'm just going to recreate it up here. So, am I sharing? I'm going to stop you. Okay, and you actually don't need your Chromebooks anymore, so you can close them up. So the battery is a can. Actually, make it slightly larger. It's a can, and it's a can made out of zinc. I'm talking. This is the carbon zinc dry cell. It's called the carbon zinc dry cell. Okay, you got a can made out of zinc. All right, and inside the can. Where are my markers down here? Inside that, I'll never test you on this. You don't have to. You really don't have to write this stuff down. I'm never going to test you on. You got a whole bunch of stuff, okay, called electrolytes, okay, and it turns out to be a paste of manganese dioxide, right? And right down the center, you got a rod made out of carbon, okay. So they call it the carbon zinc cell. And what happens is the zinc dissolves into the electrolyte paste, all right? It dissolves in and becomes a zinc ion. Christina, you really don't need that anymore. So, okay. So it becomes a zinc ion. And when it does, it leaves two electrons behind. So when the zinc dissolves into the +2, it leaves two electrons behind. So the outside becomes negatively charged. Now down the carbon rod, there's another series of chemical reactions that I don't remember. It becomes positively charged. Now these can't get to these because they're separated by a separator of some kind. It used to be cardboard, but I don't know what they use now, honestly. But if you connect them if you connect it externally, okay, then electrons can flow. Then electrons can flow from negative to positive. And that's what's going to happen when I connect this with a wire like this. Okay, I'm going to use this little trough thing to help me support it like that. Now electrons are going to move, but that's not really doing anything for me. By the way, if that screen blocks it, just move. Okay, because I'm doing everything here today, so feel free to move. All right. Okay. Now that's not really doing anything for me though. So I want to make them do work by sending them through like a light bulb. Okay, I'm going to send the electrons through a light bulb. And when the electrons pass through the filament of the bulb, the resistance of the bulb is going to cause the filament to heat up to the point where it's going to glow. And we get light out, right? So when I put a light bulb in the way, okay, then I can have to do work for me, okay, in this particular case. And that's how a battery works. Now, the zinc keeps on dissolving into the electrolyte base. Occasionally, it can actually eat away, and there's a hole in the outside of the can, and then the batteries leak, right? And the battery. So that's what happens there. So if you took a battery apart, and looked at the inside, then it'd be all pitted, at the very end. By the way, this battery looks like this. Really? Huh. I was wondering if it actually did. So I cut one open. Okay. And when I cut one open, right, it looks like this. Okay. When you guys are at home, next time you're here, I'll pass this around and you can see. All right, there's a zinc can you can see, the carbon rod you can see, then this black stuff electrolyte paste. All right, don't chew on that because it's poisonous. Okay, so don't have it for lunch. All right, so just kind of pass it around. Have a look at that. That's what a battery looks like on the inside. All right. Okay, now, how can I get, yeah, go ahead.
How does corrosion happen?
Well, because the zinc literally is dissolving into the paste. Okay, so the inside of the can gets corroded. Okay, there's less zinc and then less zinc and then less zinc and less zinc because it all goes into here, right? And so the inside gets corroded away, even to the point of getting a little hole. Okay. All right. Now, how can I get, this is pretty wimpy, how can I get more light out of that? Well, how about using another battery? Will that work? Let's find out. Oh, by the way, before I say that, this particular chemical reaction produces electrons that have 1.5 volts of energy. Okay. Now there's a whole branch of chemistry called electrochemistry. There's lots of different kinds of batteries. This particular one produces electrons, the carbon zinc dry cell produces electrons that have 1.5 volts of energy, just from the nature of the chemical reaction. Okay. So this is 1.5 volts. There's somewhere on here that says 1.5 volts. What if I want to get more out of that? Well, how about let's do this? Let's use two of them. Okay. Now, by putting the batteries in series, I get 1.5 volts. I get 1.5 volts. I get 3 volts. All right. That's kind of fun. Let's do it again. What do we have now? Glass 4.5. What do we have now? 6. Okay. Feel free to move, Christine, if you want to. Okay, all the action's going to happen right here. I hate that the screen blocks. All right. Yeah. So by stringing them together,
I'm handing out cards for your advisory class.
Okay.
How many people do you have in your advisory?
Well, depending on how many, I think about 7. Hold on a second. You got it marked.
Okay,
No, I don't. 7 should be good.
okay.
If I need more, I'll come again.
Sounds good.
Thank you. So this is 6 volts right here. All right, so you can get that string in together. All right. Okay. Now, I actually have a whole bunch of different kinds of batteries. I got that one, and I got one of these. I got, oh dear, got one of these. I got one of these. I got one of these, and I got one of these. Okay, question. Which one is the strongest battery? Huh?
The biggest.
This one?
I'm gonna go with the yellow.
Sorry, that's incorrect. Is that
The yellow one.
the yellow one?
Yeah.
That's correct. Yeah. That's correct. You guys go backstage, or at least go to back on stage. This one. Yeah. What's the next strongest? Of the remaining. What's the next strongest? This one? That's correct. Yay. What's the next strongest?
The last biggest.
This one? This one? Sorry, that is incorrect. This one? This one? Sorry, that is incorrect. This one? Sorry, that is incorrect.
Oh.
It's actually a trick question. They're all the same.
Oh.
Sorry, I was having fun. They're all the same. They're all the same. These are all 1.5 volts. Ready? 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 Come on. Ready? Look for the 1.5 on there. They're looking for the 1.5 volts in those little batteries. It's stamped in there somewhere. Got it? Got it? Got it? It's on there somewhere, Peyton. Ah, and we're going there. Okay. Got it? Find it? Okay. They're all 1.5 volts. Okay. Why? Why? Why do they make them all different sizes?
How long they last time.
Well, that's the net result. Yeah. But why do they make them such big sizes? You know, this, my graphing calculator, takes 4 of them, you know? Why want to put that in here? No, why not? Well, yeah, I could make it bigger, but do I want to?
No.
Do I want to carry that around all the time? No. It's inconvenient. So I'll put these little guys in here because it's more convenient. Now, okay, Jack, what's the difference between these two?
That one's gonna last longer, the bigger one.
The bigger one's going to last longer, right? Because when do batteries die?
When the zinc is all oxidized.
Or something.
Yeah.
When do chemical reactions stop?
Fine.
When one of the reactants is used up? Yeah?
Yeah.
Okay. So there's some limiting reactant, I think that's what it's called. If I remember my chemistry. There's when the chemicals run out, the battery die. There's a whole lot more chemicals in here than here. So the lifespan for this is going to be way bigger than the lifespan for this. Okay. Now they cost approximately the same. This one's probably going to last, I don't know, 5 to 10 times longer. Yeah, go ahead.
When you have multiple different batteries, does like one get used up first and then we go on to the other one?
The question was, if you have multiple batteries in a series, does one of them get used up? Yeah, there's going to be a weak link. Yeah, one of them is going to get used up first. Which one it's going to be, who knows?
And then when that one is used up, is that when something stops working?
Yeah, because if this one dies first, it's like unscrewing a light bulb in a series circuit. It just stops the whole chain. Yeah. So the whole string is dependent on the weakest one, which is why when my batteries die in here, I don't replace all 4 because I'm cheap. I try to figure out which one is the weakest one, right? Okay. So yeah, so it's convenient. Where do we put these?
Right.
No, I mean, what? Not in the trash. So yeah, when they're done. Yeah, but where do I use these? I don't use them in my graphing calculator. Where do I use these?
Big flashlight.
Yeah, flashlight. Something that I don't care if they're big, you know, I don't care, right? Yeah, so this is. All right, lock the camera. Huh. What would happen if I strung this one and this one and this one and this one? What would happen? Same result? Says Peyton. Let's find out. Only one way to find out, right? Let's string them together. Okay. Like this, and then like this. Now there are some connection issues, so what I actually have to do, prop up. I'm gonna prop this one up so that that will touch the knob of the seesaw. Just gotta prop it up. Like that. Come on. Like that. Sure. Sure. Oops, all right. Yep. What's the volt on these guys? What's the voltage of the string? 6. Yeah, 1.5, 1.5, 1.5, 1.5. Okay. So I get that going now. Oh dear. Oh, I lost the connection somewhere. Okay. This one? 6 volts. Okay. You can check this out later. All right. 6 volts. Wait a second. 6 volts. 6 volts. 6 volts. 6 volts. Yeah. Wait a minute. It's the carbon zinc cell, right? 6 volts. 6 volts. 6 volts. Huh. I wonder what this looks like on the inside. So I took it apart. What you get is that. Right. This lasts a long time, lots of chemicals in there, right? One of these fail. Don't know which one. Right? Go ahead.
Is like 1.5 like the magic number for this battery?
For this particular, is 1.5 the magic number for this particular chemical reaction? Yeah. Okay, this series of reactions, whatever they are, okay, produce electrons with 1.5 volts of energy. Yeah, that is particular to this chemical reaction. Okay, more on that in a little while. Go ahead.
Like 5 batteries, like 5 AAA or AA or 50 battery or that's just for me.
Yeah, it's just for the device to be engineered to the device that you want. The question is, yeah, so if for convenience, I'll use AAAs, knowing that their lifespan is smaller, but I'll pay the price because I don't want to carry these things or these things around. Yeah, for convenience. Okay, wait a second. 4 of these, right? 1, 2, 3, 4, 1.5, 1.5, 1.5, 1.6 volts. 6 volts. Could I run this off of here? If I hook it up to this, is it going to work? Is it going to explode? Let's find out. Only one way to find out, right? That one's positive terminal. That one's the negative terminal. I have to remember that. Okay. That one's the negative. That's the negative. There's the positive. Is this going to explode when I touch it? I hope not, because I'm sitting right over it. Nope, didn't explode. It's also running. Can you guys see it from way back there? Yeah. How long will this last? Forever. Right? Long enough, I'm ever going to use it. Okay, so you could run this with this. just 6 volts, doesn't matter, right? Okay. Nine volts. 9 volts. 9 volts. Okay, you guys can check this out later. Strongest battery of all. Now 6 volts was bright. Check out 9 volts. Really bright. Okay. Now wait a second. Wait a minute. 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, 1, 2, 3, 4, 5, 6 times 1.5, 9. Yeah. Okay. 9 volts. These batteries are so energetic. The 9 volts is enough that you can feel. If you put a 9 volt battery on your tongue, you can feel the electricity going across your tongue from one to another. I don't recommend it. It's kind of, I don't like it, but there's some. Did you ever put your tongue on a 9 volt battery? No. Yeah. Some boys will say, "Oh yeah, I do that." Girls, no way, I'm not that dumb. So, but you can feel it. They're energetic enough that you can feel. I don't recommend it because it's weird. It's like a metallic taste. It's not very pleasant, but you can do it because they're energetic enough to feel. Does that mean you could put your tongue around that? And you would, yeah, but I don't like the visual, so I'm not gonna go there. So, but yeah, you could, right? And that's 9 volts, right? Wait a second. Carbon zinc cell. 1, 2, 3, 4, 5. Wonder what this looks like on the inside. So I cut one open, and it looks like this. Six of them. Okay. Oh, sorry. My bad. Don't worry, you're not going to hurt it. You'd see 6 little itty bitty cells in there, and those all add up to 9 volts. Okay, and that's the that's a 9 volt. Okay, now 9 volt batteries like this. Where do we use these? We use these in things that need very energetic electrons, like smoke detectors, transmitters, like what we used to call walkie-talkies, our remote control cars, the stuff that need energetic electrons. Under continuous operation, they don't really last all that long because one of those cells, they're tiny, they're smaller than this. No, actually, not too far away from a AAA, but you get 6 of them there. And so under continuous operation, they don't last all that long. You tend to use these in things that you push a button and let it go, like transmitters. But yeah, sometimes you need very energetic electrons. Okay, so those are your basic carbon zinc dry cells. Now there are lots of other kinds of batteries: nickel cadmium batteries, lithium batteries, all the other stuff. You can just I'll so you there's all different kinds of batteries, and they all seem to produce electrons in the 2 volt range. At least the ones I'm aware of. They're in the 2 volt range. And of course you can stack them to get 4, 6, 8, stuff like that. For a car battery in your car, at least, not hybrids or electric cars, but gasoline powered cars, they have a 6, it's a lead oxide reaction with sulfuric acid as the electrolyte. And it produces 2 volt electrons. And there's a 6-layer sandwich in there. So it's actually 12 volts. Okay. But there's all different kinds of batteries that produce all different kinds of voltages. Now, I'm not sure what kind of batteries are cell phones, honestly, but they're rechargeable. Okay. And these are not rechargeable. Okay. Because this is a one-way reaction. Once the zinc goes into the electrolyte paste, there's no way to put it back in the can. All right. However, in rechargeable batteries, you can drive the reactions in reverse. Okay, you can reverse the reactions. Essentially, you can put the zinc back in the can. You can't do it with this one, but there are others with which you can. And so you can, they're reversible reactions. You have to drive them to do that. That's why you got to plug them in. But once you unplug it and hook up your cell phone, spontaneously, they'll react, in one direction, just like chemical reactions do. Okay. So rechargeable batteries have reversible reactions. Okay. These are not reversible. All right. So you said, well, Mr. Douglas, why do we keep making them? I don't know, because they're cheap. I don't know. They're cheap, I guess. That's the reason. Maybe someday we'll get more and more towards rechargeable batteries that they'll sell in stores. But right now, you go into the store, the most common battery they're going to have is this carbon zinc dry cell. But they're convenient. You can get all sorts of different stuff. Stack them, you get something like this. Oh, by the way, where do we use these? On like camping lanterns, that you put on a picnic table and just leave. You don't maybe carry them around, but don't carry them around very far. It's pretty heavy. So you just engineer all the different kinds for whatever purpose you want. All right. So that's battery spiel. All right, battery life. Questions, comments? I'm sorry. How big is a car battery? About the size of, let's see, about that high, about that wide, and about that deep. So like a toaster, a large toaster. All right. When you jump start a car,
Are you like connecting?
yeah, you're connecting the batteries. Yeah, if you ever use jumper cables, there's a very particular. By the way, do not do it with like a hybrid with Prius. I don't even know if you need to jump start those, but don't mess around with a Prius at all, okay? Because you can get really hurt. Okay. Okay, but if you have an old gasoline car, there's a very particular way that you need to connect the jumper cable. Because if you don't, you can cause the battery to explode, you can cause injury, or you can hurt the battery. You can hurt yourself, which is a lot worse than hurting the battery, right? So if you need a jump start, I got a better idea. Call AAA. Yeah, let them do it because they do it every day. All right. But yeah, car batteries, the sulfuric acid, if a car battery explodes, it's particularly dangerous because the sulfuric acid goes everywhere. Including, where are you when you jump a car? Where are you? Where you're hooking up jumper cables? Yeah, you're right over the top of it. You're right over the top. And if it explodes, all that sulfuric acid goes. Based with that. Yeah, go ahead.
For example, like that little light bulb, is there like a point in which the volts are too high for it and it would like burn out or like even explode?
It won't explode, but the filament will go. The glass, it's not enough to break the glass, but yeah, the filament blows apart. Shakes itself apart, really. And I was wondering, and because I inherited these bulbs, I don't know the voltage of these. I was wondering if it's going to burn out when I hook it up to this. I was pretty confident with the other ones, but I didn't know about this one. And I thought, well, only one way to find out. I got lots of these, so if it burns out, it burns out. But it didn't. So, but yeah, there will be. If I hook this up to 12 volts, I wouldn't be at all surprised. There's going to be a point where this thing burns out. And there's a voltage rating in here, probably. My eyes aren't good enough to see it, but all right. Okay, I think there are some questions in the chat window. Perhaps I need to address. So let me get so I can read them. And those of you at home, maybe not. You're not? Nope. Okay. All right. Further questions? Am I ever going to test you on this? No. But it was still kind of informative. I know. Learned something. Yeah. Good. And it's fun. I got enough to test you on. I don't have to test you on this stuff. So. Okay. Well, that puts a wrap on the unit. All right. The next thing we're going to do is the electricity sample test. Those of you at home, you can get it from this week's Schoology folder. Those of you here, I have a copy of it right here. Okay. We're going to spend the rest of the period, which is what, 10:05, half an hour, working on this sample test. I'm going to create breakout rooms for you guys. You guys, if you want to congregate, but you got to stay 2 arm length apart. Okay. You got to 3 feet apart, all right? But if you want to talk about it, then there's a second test and the answers are on the back, okay? So you can work on this in groups, okay? Or by yourself. Friday, I'm gonna go over this, any ones that you'd like me to do. And then I'm gonna give you, I should do this in front of the camera. Friday, I'm gonna go over this, okay? Although the answers are on the back, but I'm still gonna go over a little bit. And then however long that takes, and then I'm gonna give you the collaborative test. The collaborative test is gonna be due at the end of the day, Tuesday, a week from today. Okay, at the end of the day, Tuesday. Tuesday in class, we're gonna take the individual test. It'll be a Google form, bring your Chromebooks. If you don't have a Chromebook, the library can check them out. You can go to the library and they will give you one. You'll sign for it and all that kind of stuff. But there's enough for everybody, okay? Or if you're in here, I have computers in the back of the room that you can use. So Jack, Nick, if you don't have one, if you don't want to get one, you can use one of those computers. Perfectly fine, okay? All right, okay? Okay, so yeah, so you guys have the rest of the time, you can access this. If you're on campus, you want to stop by and get a paper copy? I don't know. Well, I guess that wouldn't be till Thursday. If you want to stop by Thursday when you're here, I'll give you a copy of this, okay? But yeah, you have the rest of the time. And let me know if you have any questions. Okay, stop recording.